research with you, which is aimed at finding a cure for PKU. I work As Scott mentioned, I work in Dr. Carrie Harding's lab at Oregon Health and Science University. Yes, go JSU. And I am working on gene therapy. And I'm very excited to tell you about a project that I've been working on, a promising gene editing approach for PKU. Now, before I move on, I want to emphasize that all of the work that I'm going to show you tonight was funded 100% by the National PKU Alliance from people like you at events like this. So let's get to it. Let's put our biology hats on right now. What's gene therapy? It's pretty self-explanatory in a sense, but it is essentially using genetic material, or DNA, as a drug, or a therapy, as it says. And there are a couple different flavors of gene therapy, a couple of different approaches that we can take as scientists. We can supply a functional copy back to the cells that the cells can then use as a template to make a functional enzyme, or we can supply the machinery to repair the mutation that causes PKU in the first place. Now you may be thinking, how do we deliver this DNA to our cells? We hijack a virus called adeno-associated virus. And this is not to be confused with adenovirus that's gotten a lot of bad press in the news. Adeno-associated virus has no known human disease, meaning it is what we call non-pathogenic. It is completely safe in humans. And in fact, it's been completed in over 130 clinical trials in the United States to date with no adverse reactions. So it is ideal in terms of its use for clinical application. Now, how do we do PKU gene therapy? How do we combine these things together? What we do is we take a therapeutic DNA, we package it into this small, non-pathogenic virus, and we let it do what it has evolved over thousands of years to do, which is deliver DNA to the cells, which can then use the DNA for some sort of therapeutic outcome. There are a couple of different approaches for PKU gene therapy. And the gene addition approach, we supply a functional copy of the phenylalanine hydroxylase gene to the liver cells. And the liver cells can then use this functional copy as a template to make a functional phenylalanine hydroxylase enzyme. Now, in the context of the mouse, this therapy is temporary. And this has to do with the biology of how this virus delivers the DNA to the cells. It delivers it as free-floating circles. And our liver, as it acquires damage over time, including by imbibing in beautiful alcoholic beverages, these free-floating circles are lost. So the therapy is lost over time. When I came to Dr. Harding's lab, I wanted to address this temporary nature of PKU gene therapy directly. I wanted to come up with something that was more permanent. And that is what put my focus on gene editing. Gene editing essentially is addressing the mutation at the ground level. What we're doing is we're packaging the machinery into this virus that is delivered to the cells and corrects the pathogenic mutation that causes PKU in the first place in the genome, which will not go away over time. This is a permanent therapeutic effect.
Oh yeah.
Now let me introduce you to our model. And no, I don't mean Kate Moss, but Kate Mouse. So the middle mouse is a PKU mouse. You can see that she's sporting a light brown fur coat. This actually has to do with the high levels of phenylalanine in her body preventing the proper production of melanin, or pigment. To her side, you can see what we expect her coat color to be according to her genetic makeup. And to her other side, you can see a PKU mouse that has a partial correction. So she has both a combination of dark and light brown fur. This is important, so just keep this in mind as we go on. So let's reiterate what we're talking about here in this therapeutic experiment. We are packaging the DNA for the editing machinery into this virus. This virus is going to deliver it to the cells that it needs to and correct the mutation in the genome, resulting in a permanent correction in terms of a therapeutic efficacy that won't go away over time. Now, how are we going to do this? I keep talking about gene editing. Who has heard of CRISPR-Cas9? Folks? You folks? Yeah? Who watches 60 Minutes? They kind of did a segment on this, so right on. Thank you, Scott. Even though it was your peer, Bill Whitaker. That's okay. So for those of you that haven't heard of CRISPR-Cas9, you can think about it like this. Think about it like a doctor performing surgery. When a doctor his hand is guiding the scalpel and telling the scalpel exactly where to cut. Similarly with this system, we provide a molecular guide. So we guide this Cas9 enzyme to a very specific location in the genome, right next to the PKU mutation in our model mice. At which point, our Cas9 enzyme, or our scalpel, will then slice through the DNA. Now, our cells do not like sliced DNA. So the alarms and the whistles are blown, and all of the repair machinery is brought to this site. At which point, the cell will use a repair template that we will provide as a part of this therapy to incorporate a functional copy of the enzyme at the DNA level. So what we do in our mice, and the mice that I'm going to show you data on in a slide or two, we inject them as neonates, and we inject them as adolescents, and then we harvest them as adults for molecular analyses. And it's important to note that when we bring this therapy into the clinic, it's going to be an infusion in a one-time single infusion into people. And our results are very promising. So let me just work you through this slide. Now I want you to note, before we go through this data, that all of these mice are on a standard chow. That's 21% protein by weight. That is the equivalent of humans eating a well-rounded diet that includes pizza and hamburgers and hot dogs. So, So mice phenylalanine levels run a little bit higher than humans that are unaffected with PKU. They're around 3 milligrams per deciliter. PKU mice, the PKU mice that we use for this study, they have very classical PKU. They're over 40 very regularly, and they exhibit all of the symptoms of PKU. Now our CRISPR-treated mice, with the paradigm that I just showed you, had a correction of down to an average of 11 with a range of 3 to 19 milligrams per deciliter. Now let's just think about that for a second. What does that mean for our children in the room to be reduced from 40 down to 11 in a single therapy? That's a dramatic improvement in the quality of life. And we're not stopping here. This is a preliminary study. We're only going down from here, right? Down to 1. And we looked at other areas molecularly in terms of the DNA and the PAH enzyme activity, and both we saw quite a bit of correction. And this is where I want to bring you back to the code color. Every single mouse that we injected with this gene therapy approach is indistinguishable from an unaffected mouse in terms of its code color. Every single one. So what's next? Obviously, we want to get this therapy into the clinic for our kids and our current patients that have PKU, so we can avoid things like maternal PKU, so our kids can be lifted from the burdens. And you may be thinking, Daelyn, come on, be real. The FDA FDA will never approve gene editing in the United States. Well, what if I told you they already did, and it's already happening? With a different enzyme system, gene editing is already occurring in the United States for genetic disorders. And CRISPR-Cas9 is currently under approval for the FDA investigatory new drug discovery for genetic disorders right now. This is going to be in the clinic within a year. CRISPR-Cas9 is going to be in the clinic in a year. And furthermore, after decades and decades of gene therapy research, we finally, this year, have our first FDA-approved gene therapy in the United States. This is huge. Thank you. But what this means for us here tonight is that the floodgates are open. They're open, and we need to be poised and ready for a therapy for PKU to come into the clinic when it's our turn. Right? Yeah. And right now, we're tackling this mountain in our preclinical model, in mice. But we have some work to do. We have to get these phenylalanine levels down to normal. We want them at 1. We need to make this approach broadly applicable to every human PKU genotype so that this therapy is applicable to everybody. And then thirdly, we have to scale this up from a teeny tiny mouse to the human body. And all of that requires generous funds because Scott nailed it. The NIH, the government, does not fund this research. This is all from us. This is my mentor, Dr. Carrie Harding, who unfortunately couldn't make it tonight. And our lab is genuinely and sincerely committed to advancing the dream for PKU. And I'm going to kind of quote Christine Brown from the National PKU Alliance here, that our goal is to have a cure that will bring the phenylalanine levels to a normal range, that will allow our children to live normal lives without worrying about PKU or their diet or the consequences of what they put in their mouth for the rest of their life. If I leave you with anything here tonight, it should be hope. Hope that we're not giving up, and neither should you.
Ladies and gentlemen, give it up for Daelyn Richards, and more importantly, give it up for all of our researchers.